This is lesson 4.4.1 for Math 1100. Both of these learning targets, we're going to do two learning targets, 4.4.1 and 4.4.2. These are just review topics from Math 1050 that will help us better understand what's coming up in 4.5 and 4.6. So a couple of things to review. We have this natural exponential function. I say natural because it's the base e, the natural number. This is exponential form. This is logarithmic form. One thing you practiced in Math 1050 was to convert back and forth if we had something in exponential form, convert it to logarithmic form, or vice versa if it's in logarithmic form, to write it in exponential form. The thing to remember here is, for example, if it's in exponential form, to get it into logarithmic form, we need to cancel the exponential part of this or rewrite so that it's not in exponential form. It's an exponential form that has a base and the variable is the exponent. So if I want to cancel the exponential form, I need to cancel a base. Now I ask this question probably 100 times when I instruct Math 1050, what cancels a base? And I ask it so often, hopefully my students remember, it's a logarithm that cancels a base. If I want to cancel a base, I use a logarithm. What specific logarithm cancels a base e? And it's the natural log. So if I use a natural log here and here, then the natural log cancels a base e, leaving natural log of y equals x. Okay? That's going from exponential form to logarithmic form. Now if I want to go backwards and go from logarithmic form to exponential form, then I want to cancel this logarithm. What cancels a logarithm? A base. And you have to use the same base as the base of this logarithm. Now this is natural log. Natural log is base e logarithm. So if I want to cancel natural log, then I'm going to use a base e. And base e and a base e with an exponent of natural log are inverse operations. They cancel each other out. So we're left with y equals e to the x, which is what we have here. So that's a brief review of some Math 1050 topics there. The other one, quickly to review, is the graph y equals natural log of x. And most importantly, the domain. The domain of any logarithm is 0 to infinity. So you can see here, there's a natural vertical asymptote at x equals 0, and the graph is completely to the right. So all values of x are positive with natural log of x. The y-intercept, or the x-intercept rather, is 1, 0. Okay, but most importantly, the domain is from 0 to infinity. It's important to recall. For this particular lesson, 4.4.1, these three rules or properties are going to be most important to recall. So these properties of logarithms. So go ahead and pause it and write these three properties down. This is the product property, this is the quotient property, and this is the power property. So what this is saying is you have a product inside of a logarithm, you expand that into two separate logarithms with a plus sign. It's the sum of two logarithms. If there's a quotient inside of a logarithm, then you expand that using the difference of two logarithms. Okay? And it's important that the numerator term is the first logarithm. The denominator term appears in the second logarithm. And then we have this power rule here. This natural log has a base e, but this exponential expression has a base x. Those don't have the same base. So this natural log does not cancel that base x. However, the power rule says you can move the exponent down in front of the logarithm here. We're going to be using these rules quite a bit in the examples for today. Okay, so part A, expand this logarithmic expression into several logarithms. Now you can see that we have a quotient. First and foremost, we have a quotient inside of a logarithm, so we're going to make use of the quotient property. Okay, we're going to separate this expression into two logarithmic expressions with a minus sign in between. So we're going to have natural log of x minus natural log of the denominator y times z. Now you notice in this logarithmic expression there's a product, y times z, so we're going to now make use of the product property and we're going to expand that logarithm into two more logarithms with a plus sign in between. So we're going to have natural log of x minus, now this is quite often a mistake I see students make. We're subtracting this entire logarithmic expression. When we expand it into 2, we still have to ensure that we're subtracting the entire logarithmic expression. So the way we do that is in a parenthesis, natural log of y plus natural log of z. And you can either keep it like that or distribute the minus sign, natural log of y minus natural log of z. And this would be the complete expansion of what we started with. So these two expressions are equal to each other numerically speaking. This is called condensed form, this is called expanded form. And by the way, the reason that we're practicing this again is in section 4.5, we're going to be looking at the derivative of the natural log, and it's much more difficult to differentiate a condensed version of a natural log as opposed to an expanded version. So we expand the natural log into several logarithms, making it much easier to differentiate. Okay, part B is going to be a little more complicated. The thing to remember here is that logarithms and radicals don't mix well. So we're going to change this radical into an exponent. So that's the first thing we're going to do. Natural log of this expression, and then the exponent is going to be an exponent of 1/3. Now there's a couple rules we're going to have to apply here. First, we have a logarithm of some kind of exponential function being raised to an exponent of 1/3. The bases don't match here. This is, remember, base e. This is a base here. So the natural log is not going to cancel this base, but I can move this exponent down in front. So that's my first task, is move the exponent down in front. Now I have a quotient that can be expanded using the quotient rule. So I'm going to create two logarithms separated by a minus sign. Now this coefficient of 1/3 is going to carry over to both of the newly formed logarithms. So it's going to be 1/3 times the natural log of 5x minus 1/3 times the natural log of x minus 1. Now you notice here in this logarithm, now I have a product, 5 times x. So I'm going to expand this using the product rule into two more logarithms separated by a plus sign. And again, this coefficient of 1/3 is going to carry over to both of the new logarithms. So this is going to be 1/3 times the natural log of 5 plus 1/3 times the natural log of x minus 1/3 times the natural log of x minus 1. And this would be the fully expanded form of that. So that's it for that learning target. Moving on to the second learning target, and again, this is a review from some topics for Math 1050, solving exponential and logarithmic equations. And more so, this is to help review properties of exponentials and logarithms that we're going to be using when we find the derivative. So we have an exponential equation. It's exponential equation because the variable is the exponent. We can't solve for an exponent if it is, we can't solve for a variable rather if it's an exponent. So the way that we get this to not be an exponent is to cancel the base. And again, what cancels base is a logarithm, and you have to have the same matching logarithm as this base. So if this is a base e, we're going to have to use a logarithm with a base e, which is a natural log. Now there's a few steps here. If you see these two examples and compare example A to example B, the first task isn't actually to cancel the base. The first task is to isolate the exponential term. So the exponential term here is the base exponent pair. That needs to be fully isolated before you use natural log. Now there's no coefficient in front, and there's nothing adding to it out here. So this is already fully isolated. We can go ahead and cancel the base e. But with this problem here, we've got to get rid of this minus 6, and then get rid of this 2 that's multiplying before we can isolate this exponential term and use a logarithm. So step 1 would be to isolate the exponential term. Okay, step 2 is to cancel the base using a logarithm. So for part A, we're already isolated with the exponential term, so I'm just going to go ahead and jump straight to using the logarithm, natural log ln. Natural log cancels base e. So now this negative 0.5x is no longer an exponent because there's no base. So it's just negative 0.5x equals natural log of 0.075. So again, step 1 is to isolate the exponential term. Step 2 is to cancel the base using a logarithm. Step 3 now is just to solve for x. The only thing left to do is divide by the coefficient. So x equals natural log of 0.075 divided by negative 0.5. Okay, so for this one, we have to do a couple of steps before we can use a natural log. Got to isolate the exponential term. It's going to add 6 to both sides. So now we have 2 times e to the 3x minus 7 equals 9. Now we need to get rid of that coefficient of 2 to isolate the exponential term, so divide by 2. And we have e to the 3x minus 7 equals 9/2. Now the exponential term is isolated, so now we can cancel the base of that exponential term using a natural log. Natural log cancels base e. So now this exponent is no longer an exponent because the base has been canceled, so it's just an algebraic expression, 3x minus 7, and that's equal to natural log of 9/2. Now we're to the final stage of this, is just solving for x. So if we add 7 and then divide by 3, we're going to have x equals natural log of 9/2, and then we add the 7 and divide the whole thing by 3, and that's the exact form of the answer. Now I say exact form. If we wanted the approximate decimal form, you'd have to get on your scientific calculator, figure out the natural log of 9/2, then add 7, divide by 3. It would give you a decimal approximation of that. Now part C, we're moving into solving logarithmic equations. So we're solving for x. X is part of an expression that's inside of this natural log, so we can't solve for x as long as this natural log is here. So we need to cancel a natural log. Well, what cancels a logarithm is a base. But we still could run across the same thing with exponential terms, is we have to isolate it first. For example, this equation, the natural log, is already isolated on the left side of the equation. But for this problem here, part D, this natural log expression is not isolated. We have a plus 6 here, and it's multiplied by 3. So the first step here is to isolate the logarithmic term. It's already done on part C, so we don't need to worry about that. Once the logarithmic term is isolated, you cancel the logarithm using a base. Now it's important they write this correctly. I've seen students write it like this. E times natural log does not cancel each other out. If you use a base e and natural log is the exponent, those are inverse functions. Those cancel each other out. So you have to make sure that you write it correctly as a base exponent, not multiplying as a coefficient. So e raised to the natural log cancels out. So the 4x is no longer inside of a logarithm. So we have 4x equals e to the 1.6 power. And final step is to solve for x. Divide by 4. So x is equal, and again, that's the exact form. If you want the decimal approximation, you would use your scientific calculator, use a base e, raise it to a power of 1.6, divided by 4, give you a decimal approximation. Part D, the exponential term is right here, natural log of x. It's not isolated, so we're going to have to move these terms to the other side of the equation. So first you have to subtract 6, and then divide by 3. So we're going to have natural log of x. Now 8 minus 6 is 2, and then 2 divided by 3 is 2/3. So we've isolated the logarithmic term. The next step then would be to get rid of the logarithm using a base, in this case base e. So base e cancels logarithm. Base e cancels a natural logarithm rather, and we have x equals e to the 2/3 power. And there isn't a coefficient of x or anything after it that we need to move over. So x has been solved. The equation rather has been solved, and the solution is x equals e to the 2/3. So again, hopefully these topics are familiar to you. They're topics from Math 1050. So it's an important review, and these skills are important to help students be successful in later sections in Chapter 4.